This video is going to cover limits at infinity. We're going to talk about how we prove limits to infinity as x approaches infinity or negative infinity algebraically. Okay, so the target is students will determine the limit of a function as it approaches positive or negative infinity using algebraic methods to gain an understanding of the rules of horizontal asymptotes learned in Algebra 2. Okay. So the first time we talk or you learn about horizontal asymptotes is in Algebra 2 when you start talking about rational functions. That extends to pre-cal when we start talking about the idea of end behavior. So I'm going to grab a pen, let's get a different color. Okay. So if we think about the idea of this rational function up here, okay, how do we determine what the horizontal asymptote is? In Algebra 2, you learned 3 rules to help you determine what the horizontal asymptote was. So they said to look at the largest term with the highest degree, so that would be our x to the 7th right here, and our negative 6x to the 7th right here. It says if the numerator degree is equal to the denominator, then the horizontal asymptote occurred where y is equal to the ratio of the coefficients of the highest power. So in this case, our x to the 7th and our x to the 7th are the same degree, so we look at our leading coefficients. The second rule said if the numerator was less than the degree of the denominator, then the horizontal asymptote occurred at y equals 0. We call this bottom heavy. That just means we have more value going on in the denominator. And then the third one said if the numerator is greater than the denominator degree, then the horizontal asymptote did not exist. So this is what we consider to be top heavy when it comes to the degree, the highest exponent. Okay, it did not exist for us. We didn't have a horizontal asymptote, and what that meant was our end behavior was going to positive infinity or negative infinity, or it just did not exist to end with. So the question is, how do those rules, and why are the rules those rules, and how does it relate to calculus? So if we think about the idea of approaching infinity and negative infinity, that's the idea of a limit. Okay, so I'm going to prove, if we look at the top one, the one that I circled at the top, we know that our horizontal asymptote happens to be at y equals positive 1 over negative 6, because our degrees were the same. Okay, but if we think about the idea of a limit, and looking at the limit as we approach infinity, because that's what the horizontal asymptote is that end behavior, how do we algebraically prove that this is in fact 1 over negative 6? That takes a little bit of manipulation. So if we think about the highest power, the term with the highest power, that's that x to the 7th. If I can get everything away, divide out that x to the 7th and deal with just what I need to look at, the highest terms itself, I can algebraically manipulate that. And what I'm going to do is divide the top, or multiply by 1 over x to the 7th. I'm going to do that same thing to the bottom. And all I'm doing is multiplying by 1 here. But I'm trying to factor out or divide out that idea of x to the 7th. Because that's our largest term. When we talk about infinity, we're talking about large values. Therefore, we're looking at our largest term. Okay. If I just do some distribution, I'll get something like x to the 7th over x to the 7th plus 5x over x to the 7th. So all I'm doing is distributing this 1 over x to the 7th. And I'm going to do the same thing to the bottom. Now you might be thinking, why am I doing this? And what I'm trying to do is I'm trying to isolate that highest term. I'm trying to divide it out, get it out of the way. And I'm doing that through that division. So I'm just going to simplify this really quickly. In our numerator, we'll get 1, because x to the 7th over x to the 7th gives us 1. I'll get 5 over x to the 6, using my properties of exponents. That will remain 14 over x to the 7th. On the bottom, get 3 over x to the 6 minus This reduces down to 6 minus 2 over x to the 7th. Now, if we think about these fractions, this 5 over x to the 6th, negative 14 over x to the 7th, and we're looking at x as it's approaching positive infinity. And what that means for us is that our denominator for this fraction, our denominator is growing really, really, really large. And when that happens, when our denominator is growing really, really, really large, that means the value of the fraction is incredibly small. So small that we would say that it approaches 0. As denominator approaches the largest number possible, our numerator in our total fraction is going to approach 0. If that's the case, so does this one. So does this one. And so does this one. And if we see what we have left, all we have left in our numerator is just value, 1 over negative 6. Okay, and that's exactly where we said we were going to get from the very beginning, if we think about it, what I put up at the top here. Let me get a pen. Sorry, I'm having some issues. So that pen, or that value right there of y equals 1 over negative 6. Algebraically, what I did at the bottom is what's really happening. Now, that's not something I expect to be done on every problem, but just the idea of it. Dividing out our largest term. And dividing out our largest term gives us that idea of that leading coefficient because our numerator and our degree of our denominator were exactly the same. Now, if we think about this, that goes back to what the definition of, let me get down. The definition of a horizontal asymptote. The true definition of a horizontal asymptote says the line y equals L, L being some numerical value, is a horizontal asymptote of the graph if the limit as x approaches infinity or the limit as x approaches negative infinity is that value. So the definition of a horizontal asymptote is based on the limit as we approach positive infinity and negative infinity. What that means too, if there is no horizontal asymptote, like the last row from the top, then that means that our limit as x approaches either positive or negative infinity of the function does not exist. Okay, and we know there's two reasons. Of course, we wouldn't talk about oscillation here, but there's two main reasons why a limit as we approach positive infinity or negative infinity does not exist. And that's because either we're approaching positive or negative infinity, or there's some oscillation going on, as you'll see with an example coming up. Okay. So when we're approaching limits to infinity, I did a lot of work at that top one. I would never expect you to ever do that work. What I do expect is for us to know the rules, because the rules make it a lot faster, where it's pretty much very, very little work when it comes to limits to infinity. One of the things that we may have to do with limits to infinity, however, is simplify them, like this problem right here. Okay, in order to determine what rule to follow, I have to make sure that I am in simplified form, so no parentheses. So I'm just going to distribute that real quick. Get 2x to the 4th minus 2x cubed all over, and I'll get 6x cubed minus 2x squared plus 3x minus 1. And what I'm looking for is the term in my numerator and my denominator with the highest exponent. So in this case, that's that term, and in the denominator, it's that term. And if we can see our numerator is greater than our denominator. Okay, and what that means for our limit is, in fact, it does not exist. And going back to those three rules at the top. Okay. Our numerator is greater than our denominator, therefore I do not have a horizontal asymptote. It doesn't exist because of that limit to infinity. And for this reasoning, that's because we're going to positive infinity. If we think about those two terms and we plug in this idea of positive infinity, we're going to get a really large positive number in the numerator and a really large positive number in the denominator. Okay. And of course, our numerator is always going to be greater because it has higher power. Okay. Let's go to the next page. I'm going to do 2 on here really quickly, and then we're going to save the other 2 for class. So I'm going to save the top 2 for class, but I'm going to do the 2 on the bottom. Okay, so again, the first thing I'm going to look at is my highest term on top, highest term on bottom. So my numerator greater than my denominator, which automatically means for us D and E. Okay, and if we look at it, we're going to positive infinity, so that's going to give us a positive infinity on top, positive infinity on bottom, so it's going to go to positive infinity overall. Okay, if we look at the next one, this one can be simplified, so I'm going to do that really quickly. As x goes to infinity, I get 2x to the third on top, x to the fifth on bottom. And in this case, my denominator is greater than my numerator. Therefore, this is going to equal 0. Because my denominator, if we think about it again, my denominator is going to grow a lot larger, a lot faster than my numerator. Therefore, that value of that fraction is going to get really, really small and approach 0. Okay, so we're going to stop there. Those last 2 examples we'll do in class. If you have any questions, come see me in the morning.